simple harmonic oscillations. Let's begin with a horizontal, uncompressed spring that is at rest on a table. As you can see, a small object is attached to the spring. We'll assume that there are no energy losses due to friction. If we compress this spring and release it, it will oscillate back and forth horizontally. Let's analyze these oscillations in more detail. We said that when we start our timer, so at t equals 0 seconds, the spring is fully compressed. As time passes, this is what we see after 1 second, after 2 seconds, 3 seconds, and 4 seconds. So for this particular object and spring, it takes 4 seconds to complete a full cycle or oscillation. The time it takes for the object to complete one full cycle or oscillation is called time period. Another related word here is frequency, which is defined as the number of cycles or oscillations completed per unit time, usually per second. This is the formula connecting time period and frequency, and for completeness, here are the variables. As we mentioned, the time period for this oscillation is 4 seconds. Rearranging the formula above for frequency, we get f is equal to 1 over t or 1 over 4 seconds. This is equal to 0.25, and since we are dividing by seconds, the unit is seconds to the power of -1 or per second. A unit that is more commonly used for frequency is the hertz. Let's continue by adding a simple scale to our diagram. At the center of this scale, the object is passing through the position where it was originally before we compressed the spring. This position is called the equilibrium position. You can see here that during one complete oscillation, the object passes through the equilibrium position twice. We'll talk more about the equilibrium position when we get to simple harmonic motion in the next few videos. The two extremes on this scale, so where the spring is most stretched and most compressed, are called maximum displacement positions. This is the farthest that the object gets from the equilibrium position. We usually label the equilibrium position with 0. We'll discuss this further when we graph simple harmonic motion. Let's assume that here, when the spring is stretched to its maximum, the object is 20 centimeters away from the equilibrium position. This means that when the spring is most compressed, the object is also 20 centimeters away from the equilibrium position, but in the opposite direction. I will denote this position by -20 centimeters. So we can say that at t equals 0 seconds, the displacement is -20 centimeters. At t equals 1 second, it is 0 centimeters. At t equals 2 seconds, it is 20 centimeters. At 3 seconds, it is 0 again. And at 4 seconds, it is -20 centimeters. The final concept to mention here is amplitude, which is the distance between the equilibrium and the maximum displacement position. It doesn't matter which maximum displacement position we use here. Since amplitude is a distance, it is always positive. The amplitude for this situation is 20 centimeters. This completes the introduction to simple harmonic oscillations. The object in our example here undergoes simple harmonic motion. In the next video, we'll learn about simple harmonic motion in more detail.